The derivation for the potential energy function for a dipole in a uniform electric field should now be much more easily understood now that we understand that we have a minimum potential energy when the P vector is aligned with the E field. So this is going to be our potential energy min, right? When the P vector is rotated counterclockwise, we get a potential energy max back here, right? So we have a PE max. And when we're right at 90 degrees, we're at our halfway point. So this is going to be the 1/2, right? The 1/2 potential energy point. Now, it may not seem obvious to us right away. Sure, it doesn't. But we are going to actually reference the halfway PE point as 0 joules. So halfway potential energy is always going to equal 0 joules to us. We'll talk more about that in a moment. From mechanics, however, individual joule values don't matter. As long as we're losing joule values when we are rotating to PE min, and we're gaining joule values when the P vector rotates to PE max, we're okay. All right, let's do our mathematical derivation here. Delta U equals negative the work done by the field is not an E&M equation or a mechanics equation. It is a fundamental equation to physics. So delta U equals negative the work done by the field. Work, if you remember from mechanics, F dot delta x, or integral F dot dx. The rotational version, instead of integral F dot dx, becomes the integral torque dot d theta. Right? So we get the torque dot d theta. And if you recall from what we did in mechanics, we did our derivation for potential energy with loading the system, increasing potential energy. So if our initial potential energy is here at 90 degrees, right? That's going to be our reference potential energy of 0. And we're going to load the system by rotating it counterclockwise. So our theta final corresponds to a d theta that's counterclockwise. Torque is always P cross E, trying to rotate that P vector to align with the E vector. So that's going to be a clockwise torque. That's where we get our cosine of 180 degrees, or -1. And now we can do delta U equals the torque, where our negative in our torque equation, a negative from our dot product, -1, is the negative I have shown here. Our torque, right, is PE sine theta. I can do that in blue, I think. So the PE sine theta, that whole thing, do it this way. That PE sine theta, that whole thing, right, is the torque. And then we have our d theta. So we're color coding it. That's the torque. That's the d theta. All right, well, as it says here, recall that the integral of sine d theta is negative cosine theta. So just like in mechanics, we had that darn negative to track down. I have my two highlighted negatives here. The negative from the definition for delta U is negative the work done by the field. The negative from the cosine of 180, the -1. And then another negative, right, from the integral of sine to cosine is the purple negative here. So that's where our final negative comes from. We do final minus initial. Cosine of 90 degrees is 0, and there's our reference. That's why it is convenient to use it as 0 degrees or 0 joules. Otherwise, I would have to add a constant term to this basic equation. So the potential energy function, right, since U initial is referenced to 0, the potential energy function, negative PE cosine theta, and I have it exploded because that's my go-to equation when I actually calculate. So the general boxed equation, the one you'll see in the textbooks, is that potential energy, of course, negative PE cosine theta is negative P dot E, so that is of course, correct, but we will always, when I problem solve for my solutions, you will be seeing this equation constantly. And that equation is so important because of this reference at the bottom that is stating for you to remember that it is really important that delta U is all that matters, right? Because it's the loss of potential energy, that negative delta U, that is going to give us that positive change, the change in kinetic energy that we calculate. So how much of the potential energy is being converted into kinetic energy. Again, you do not need to memorize this as a derivation, but when we pick up and use this red exploded equation constantly, I think having a better feel for where it came from makes its application easier, which we are now going to do in our next notes.